All right, I want to explain the unary operations of differentiation and integration of matrices. Again, unary operations mean something we can do to one matrix. So if we're given a matrix of functions, let me write A of t. So these functions, inside of it will be functions of t. So we define the derivative of this matrix to be the matrix whose ij entry is the derivative with respect to t of the ij entry of the matrix A. So we just take derivatives of the components one at a time. Similarly, we'll define the integral of A of t, say from B to C, to be the matrix whose ij entry is the integral from B to C of what the ij entry of A was. So for example, let's let A of t be the matrix e to the 2t 1 0 1 plus t. Then the derivative with respect to t of the matrix, which I guess I could write as A prime of t, is we just take the derivatives of all the components and write them down. So derivative of e to the 2t is 2e to the 2t. Derivative of 1 is 0. Derivative of 0 is 0. Derivative of 1 plus t is 1. And let's take the integral of this matrix from 1 to negative 1. I guess I have a little bit room here so I can write. So the integral from negative 1 to 1 of A of t dt is, we'll just take the integrals of each of these components. So the integral of e to the 2t from negative 1 to 1, the integral of 1 dt from negative 1 to 1, and the integral of 0 is just 0, and the integral of 1 plus t. Now the integral of e to the 2t, I guess I'm running out of room here. Let me go back to the top. Is e to the 2t over 2. E to the, I can get rid of the integral sign, e to the 2t over 2, evaluated from negative 1 to 1. And then we have the integral of dt is going to be t, evaluated from negative 1 to 1, and 0, and we've got t plus t squared over 2, evaluated from negative 1 to 1. So this will be e to the 2 e squared over 2 minus e to the negative 2 over 2. So e squared minus e to the negative 2 all over 2. T from 1 to negative 1 is 0. and then 0. And what do we get when we evaluate t plus t squared over 2 from 1 to negative 1? Let's see, so 1 plus 1/2 minus negative 1 plus 1/2. So 1 plus 1 is 2. 1/2 minus 1/2 is 0, so that's just 2. So that's the integral of a of t evaluated from negative 1 to 1. Now recall from calculus that we have a product rule for derivatives. If we want to take the derivative of f of t, g of t, that's derivative of the first times the second plus the first times derivative of the second. And it turns out that the product rule works for matrices also. So if we have a of t, b of t, the matrix product, the derivative is going to be derivative of the first times the second plus the first times derivative of the second. And let's see why that's true. Let's let C of t be the matrix we get by multiplying A of t and B of t. Then the ij entry is a sum. Let's say these are n by n matrices. So sum sk goes from 1 to n. Well, actually, I guess they don't need to be even the same. We can multiply two matrices without having them be the same dimensions. Let's let A be m by n and B of t be n by p. So I'm still going to take, when I multiply them, the sum as k goes from 1 to n, because that's the common index between them. So we'll have aik, which is a function of t, times bkj, which is a function of t. And if we take derivatives of these entries, then we use product rule on these two functions. We'll have a prime ik of t, b kj of t, plus a ik of t, b prime kj of t. Now we're just adding things, so I can write this summation twice. I can write sum as k goes from 1 to n, a prime ik of t, b kj of t, plus the sum as k goes from 1 to n, a ik of t, b prime kj of t. And this sum we recognize from the product formula as the ij entry of a prime of t, b of t. And then this sum, for the same reason, we recognize as the ij entry of a of t, b prime of t. So if every ij entry of C has this form, I guess the matrix C is equal to this sum of products of matrices. Questo è dimostrato. The end.